Hello, my dear students of grade 7. I hope you are all well and doing fine. In today's video, inshallah, we're going to start a new chapter, chapter 16, lesson 1, reducing and detecting the sound. Before we start, we must know that sound is a longitudinal wave, which means it moves parallel to the wave direction, and it contains some parts that are where particles are closer to each other, which we call compressions, and other parts that particles are far from each other that we call wave fractions. Um, and the sound is produced is how we are going to is what we are going to learn about inshallah, and how do sound waves move from one place to another, why do sound waves travel at different speeds through different materials, like why does the wave speed changes when it travels through solids, not like the same as it travels through the air, and so on. The last but not least is what are the functions of different parts of the human. The vocabulary we're learning about are not new for you guys. I mean, you learned about them in the last chapters, chapter 15. Um, so you learned about the longitudinal wave, you know this already, the vibration, which is the rapid movement, it could be back and forth or up and down movement that causes the wave to happen. And you'll learn later that without vibration, we will never hear a sound, or the sound energy will never be produced. The medium is the material through which the wave travels. And since sound wave is a longitudinal wave which belongs to mechanical waves, sound wave cannot also travel through the vacuum or empty space. It needs a medium or particles to travel through. And compression is the part of the wave where particles are closer to each other, and rarefaction is the opposite part, or it's the opposite of the compression, which is where the part of the particles where the part of the wave where the particles are away from each other. So let's start with what is the sound. And sound waves are longitudinal wave, as you learned from last chapter, which means they can only travel through matter because longitudinal waves belong to the mechanical wave. So every sound wave is a result of a vibration. If there is no vibration, that means there is no sound. What is vibration? If you look closely at this picture, he's zooming into the strings of this guitar, and you will notice that when you pluck a guitar, it starts to vibrate or moves really fast, like back and forth movement. That, of course, can happen through different types of matter, like in solids and liquids and gases. But this vibration or this movement that we do while plucking the strings of a guitar, this is what causes the sounds to happen. So, as we said before, every sound is produced by vibration. So, the energy carried by a sound wave is caused by the vibration, as we said. What's a longitudinal wave? You already know this. It's the wave where the particles in the material or in the medium move parallel to the wave direction. So this arrow, for example, is referring to the wave direction. You will see that the energy, or I'm sorry, the longitudinal wave is moving in the same direction, not like the transverse wave where the particles move up and down or perpendicular to the wave direction. But both longitudinal wave and transverse wave, both of them belong to the mechanical wave, which are the waves that cannot move through empty space. They need a medium to move through. So how is sound produced? This is a very important question. It's produced when the object that makes the sound or causes the sound to happen vibrates, like the string of the guitar, like this skin of a drum, like when we hit the skin of a drum, it also starts vibrating, which causes the sound to be produced. Even the wind instruments that we use, like music wind instruments, where we blow the air inside the instrument, the air in there is the one that vibrates, causing the sound we're hearing. So, in order for sounds to be produced, a vibration needs to happen. What is a medium? As we said, it's the material in which the wave travel. Since we're talking about sound here, it's the material in which the sound wave travels. So it should be solid, liquid, or gas. There should be a medium because sound, as we said, is a longitudinal wave, which belongs to mechanical wave, and those are the waves that cannot travel through empty space. They need a medium to travel through or a material to travel through. So here we're saying that the sound waves cannot also travel through empty space. As we said, they carry, of course, the energy. They do not move the particles of the matter. So in here we are, of course, showing you how the particles move in order to carry the sound energy from the speaker in here. Okay, this is speaker. If you put your hand on the speaker while it's working, you will feel that it's beating back and forth. It's moving back and forth, right? And this movement is the one that forces the particles of the air or the particles of any matter through which the sound is moving to also get closer and get farther from each other, um, which of course will produce decompressions and rarefactions, which will make up a longitudinal wave. In here, we're talking about the sound wave. So this picture again, guys, shows you how the movement of the speaker, the back and forth movement of the speaker, causes the particles to also vibrate, or I'm sorry, carry the energy, causing you to hear the sound all around. What is rarefaction? It's the part of the longitudinal wave where the particles are farthest from each other. So if you looked in here, you will find that the speaker in here is moving also back and forth, right? In the compression part, the speaker cone moved out, like it moves to the outside. Okay, so this caused the particles to get closer, like he pushed the particles so they became closer to each other. In the rarefaction, the opposite happens. What happens in here is that the speaker cone goes back or moves back, causing the particles of the medium to move a little bit away from each other. Okay, just reduces low pressure, which will make the rarefaction in here. This part where particles are far from each other, and that's happened because the speaker cone, we can say the speaker in here, moved backwards, causing the rarefaction to happen. Okay. So the particles of a medium vibrate back and forth as a sound wave carries energy away from the source. The wave, guys, is always carrying the energy away from the source, not toward it. Like you talking, the sound energy will move away from your vocal cords, not toward your vocal cords. That's why we use speakers like this to call people like in a far distance. So they would, for example, like come, um, it's like call them from a really far place, and it works because the sound energy will move away from the source, not toward it. So here, you guys, you learn that sound waves travel by a longitudinal wave. They are longitudinal waves, so they travel by carrying the energy through the medium, causing compressions and rarefaction. Um, of course, you know both of them. What is the meaning of both of them? And you also learn that the sound wave travels in a parallel to the wave direction, with the wave direction. The speed of the sound is affected by two factors. Okay, the density, and density means how closely the particles are closer to each other. Okay, or how closely the particles are packed. The second thing is sound travels faster in stiff metal than a rubbery metal. That's why when I want to make any room, like soundproof. Like I want the sound to be like only inside this room. I don't want the sound to get out. You'll see in those rooms that the openings that leads outside are always covered with rubber objects, so they can stop the sound from going outside. That's because the sound moves really fast in stiff metal, like a door or something. The sound moves faster through the metal of the door. But if I'm closing it or covering this door with rubber, it will make it harder for the sound to move through it. Sound energy travels slowly in gases and faster in the solid and liquid. The sound wave also travel faster in seawater than the fresh water, and that's because the seawater contains more dissolved salt in it, which will cause higher density than fresh water. And we just learned that density, which means how closely the particles in the medium are packed, the density goes higher. That means the sound movement or the speed of the sound will also be faster or higher. Okay, and since salt water contains more salt than fresh water, obviously it will be more density. That means faster sound. So if you look in here, you find that sound travels fastest in the solids. Like in this table in here, we have glass, iron, ice. You'll find that the speed is much higher on those three objects because they are solid. But if you look closely at like air, for example, you find that it's less. Least speed of the sound is in the gases. But when we increase the temperature of the air, when it's hotter air, you'll find that the speed increased, right? And that's because the particles came closer to each other because now they have more energy, they have more temperature, which means they have more energy, and that causes the sound to move a little bit faster through it. You'll find here also in water, when it was 0 Celsius and when it was 20 Celsius. So you can see how temperature changes or affects the sound speed. So as the temperature of a gas increases, the particles, as we said, move faster and start hitting each other, colliding more often, and this will help the energy of the sound to transfer, you know, in less time. It will not take the same time as if it's cold air, for example. In the liquids, it's totally the opposite because if you go back to the table, you find that water with 20 Celsius, which means higher temperature, the speed will be 1.481, while when it's 0 Celsius, you'll find it's 1.500. So again, temperature, okay, increases when I increase temperature of gases, the sound speed will also increase. But that is where the opposite takes place in the solid and liquid. When temperature goes higher, the speed goes lower, but that only happens in solid and liquids. So why does sound travel at different speeds through different materials? So now you learned that it's at different speeds through if it's solid, if it's gas, it's liquid, if the density changes, and also if the temperature changes. Okay, this is why, because when we increase the temperature of the air particles, the particles of the air will move faster because now they have more energy, and this will cause the sound to travel way easier or takes less time than if it's cold air, where the opposite takes place in solid liquids. Detecting sound in human ear has three main parts. We will learn about this inshallah in the next session. About different parts of the air, the outer part, the medium, or the middle ear and the inner ear. So I hope you guys enjoyed this lesson. If you have any questions, please write them down. You can watch the video multiple times. Just write any questions you need me to answer when inshallah I come back. So I will answer all your questions in the next session. So see you guys next time inshallah. Stay safe. Thank you. Bye.